All right, so far in chemistry, we've looked at taking various compounds and throwing them into water and making aqueous solutions. But we haven't explained the rhyme or reason behind why something would become an aqueous solution. So this is where we get into this idea of solubility. Now, in the introduction activity that you did, you probably learned a little bit about whether something is soluble or insoluble. We're looking now at whether an ionic compound, so this is typically what we're only looking at, is ionic compounds and whether they will dissolve in water and create a soluble solution or whether they're going to be insoluble. Now, your green sheet contains some rules to kind of follow along with this. So if we look at anything here that has these various ions, so anything that's a chlorate, an acetate, a nitrate, anything that is bonded together with a group 1 metal, okay, so these are the lithiums, sodiums, potassiums, and then the ammonium ion. So anything that is one of these groups will be a soluble solution. There are no exceptions to this that would make it an insoluble compound. So if we had a substance, so if we give some various examples. So if I take potassium and put it together with acetate. So C2H3O2. When I take this substance and I drop it into a beaker of water, okay, when it goes in, it'll form ions. So we're going to see two various ions that'll form. We'll get our potassiums, so this will be our potassium piece. Okay, they'll be floating around in there. And then we'll get our acetates. Okay, so this is our acetate piece. And then we'll get 1, 2, 3, 4, 5. Okay, so they'll all split up to give us those parts. So these are the examples of what happens. You take a substance that's a solid, you dump it into water, you get an aqueous solution, and you're going to see that they'll dissociate, that they're going to separate. They can carry that electrical current. Okay, and so anything that is of this nature will always be soluble in water. Okay, now there are some that are like sulfates. So if we have a sulfate that is put together with some type of a compound, so I'm going to say a nickel sulfate. Okay, so NiCSO4. So this is our nickel 2 sulfate. Now if we take that and we dump that into some beaker with water, so it goes in there, it will be soluble again. So in other words, the nickel will form little bits that'll dissociate, as well as the sulfate piece, which will dissociate as well. Okay, and so they'll dissociate, they'll actually create an ionic solution. Okay, now there are some exceptions though to this, like if we had calcium sulfate or barium sulfate, lead sulfate, strontium sulfate, okay, any of these elements combined with a sulfate, when we tried to dump that into a beaker, so here's a beaker, again we'll put some water in there, and let's do a silver sulfate, so an AgSO4, okay, when that gets dumped in to our beaker, nothing's going to happen. It's going to stay as a chunk, okay, of Ag2SO4. It's not going to dissociate. So no dissociation, stays as a solid. That would be an insoluble compound. Okay, so we might see it, if this was a piece of crystals, or I should say like a powdered form, when we stir it in, it'll still be a powdered form. It'll settle at the bottom, and we'll see this as more of a suspension. So that's the difference here, is that those would be insoluble in a beaker. Now we do have a few other ones. So again, if we have anything that's a halogen, so anything that's a fluoride, a chloride, a bromide, or an iodide, those are going to be soluble. Here are exceptions though, like a mercury fluoride would be insoluble, a silver chloride would be insoluble, and a lead bromide would be insoluble. So these are all just different combinations that give you insoluble solutions. Okay. We also have these ones here. So these are ones that if you contain carbonates, phosphates, silicates, sulfides, chromates, or hydroxides, you're going to be insoluble in water. So this is examples of ones that would form insoluble compounds, unless they are mixed with something like a group 1 metal. So that's our lithium, sodium, potassium, rubidium, cesium, and our ammonium ion. So if you got any of these mixed together, then we know that we're going to get something that'll be a soluble solution. Chromates, and again, mixed with any of our group 1A metals. Okay, if we add in calcium, magnesium, and then the hydroxides, calcium, barium, and strontium. So this is our kind of a guide. Okay, so this is kind of our general rules that we like to follow for various situations. So let's put this kind of into practice now. Let's look at an example of a reaction. So I'm going to take a reaction of some zinc nitrate. So some zinc nitrate. And I want to make a solution out of that. And I'm going to add to that some ammonium sulfide. And I want to see what's going to happen. So the zinc nitrate, again, as a substance, okay, we look at it and we say, is that going to be soluble? So we know that any nitrate, okay, has no exception, so this is going to be soluble. So when this goes into our beaker of water, the ZnNO3, I'm going to have to put a 2 around it, okay. When we split that up, the zinc is going to dissociate. So we're going to get some particles there. The nitrate will dissociate. And now I did put 10 of the nitrates because it's 2 nitrates for every 1 zinc. So we got a lot of nitrate floating around. We got a little bit of zinc ions floating around, but these are all now ions that are in solution. And what we're going to do is we're going to compare that to a beaker that's going to contain our ammonium sulfide. Okay, again, ammonium is that NH4, so there's no exceptions here. This one will form NH4S. We're going to need to put a 2 there, and that'll make that. So again, when we dump this in, we're going to get all of our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. That's the ammonium pieces. And then we're going to have our sulfide pieces, 1, 2, 3, 4, 5. Okay, so we've got our things breaking up. We're adding those 2 beakers. So now we're going to pour everything in those beakers together. Okay, so all of the contents of this gets dumped in here. And we want to find out what's going to happen. Okay, and so when we look at this reaction, this is a double replacement reaction. So the zinc is going to change places with the sulfur. So we know that we're going to get some zinc sulfide. And we're going to get some ammonium nitrate. Now, zinc sulfide, that's just going to be the ZnS. Ammonium nitrate, NH4NO3. And when we look at this, we're going to see what happens is, if I make a comparison here, I've got that zinc with the sulfur. So any compound that contains sulfur, okay, all of our sulfides are going to be insoluble in water unless it's one of these, and it's not. So in other words, this is going to stay in the bottom as like a piece of zinc sulfide. So we'd say it precipitates out of the reaction. And then we're going to end up with that ammonium nitrate still hanging out in solution. So in other words, that's going to be hanging out in our solution as ammonium ions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those, and then we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those, and we would have those all left in here. So the ammonium ions are going to be in there, as well as the nitrate ions are going to be in there. But we would precipitate out. Now what we do is we start to write this out and show this in what we call a net ionic equation. Now really, and I should balance this out to make sure that this is balanced, I've got the 2 here is what I think I need. So Zn, Zn, and S, 2 of those, 2 of those, 2 of those, 2 of those. So this is my this is just my regular reaction. Now what I'm going to do is I'm going to show this in terms of what it's going on, or the mechanism that's inside of here. This is an aqueous solution. This was an aqueous solution. This becomes a solid precipitate, and this stays as an aqueous. So I'm just putting our phases in there as well. So again, what happens is when this gets dumped into the water, we're going to get zinc ions with a +2 charge. That'll be aqueous. We're going to get some nitrate ions. So there's 2 nitrate ions. That'll be aqueous. We then have this stuff right here, the ammonium sulfide. That'll give us a 2NH4 plus ions. And these are going to be aqueous. And then we're going to get our sulfide ions. So -2. That's going to be aqueous in solution. So these are all the ions that were present in this container. In this container, we then dump them all together, and the reaction happened where the zinc ions grabbed hold of the sulfate ions, and we formed our zinc sulfide solid. So this is the precipitate that comes out of the reaction. And then we end up with just a bunch of other ions that are going to be floating around here. So we're going to have our 2NH4 ions that'll be aqueous in solution, and our 2NO3 ions aqueous in solution. And so those ions are just floating around. Now what we do is we look at this and say, this is the overall ionic equation here that's going on. It shows that these substances, when dumped into water, became ions. They floated around as ions. And then when we mixed the two together, we got a precipitate, and we got some extra ions that were left over. Now these extra ions are what we call spectator ions. So these ions right here and these ions right here are spectators because they didn't really do anything in the reaction. It's like they weren't even there, weren't even needed. We wouldn't even see them. So what we do is we remove the spectator ions to write a net ionic equation. So really the net ionic equation is if there's any kind of substance that has some zinc ions that are aqueous and some sulfur ions that are aqueous, we will precipitate zinc sulfur. So this is my net ionic equation. So if we look again at our types of reactions here, this is called the net ionic equation. This is the complete ionic equation. And this is just our balanced reaction. So we have a reaction, we have a complete ionic equation, we have a net ionic equation. Let's look at another example. Okay, so one more example here. Let's talk about this substance. So we're going to have some barium chloride. We're going to mix it with some sodium sulfate. we're going to see what's going to happen to this reaction. So again, when I look at my chart, my barium chloride, okay, barium is in that, let's see, barium is here. Oh, but it's not part of that chloride. So chloride exceptions are mercury, silver, and lead. So those are not one of the exceptions. So this is definitely going to form an aqueous solution. The sodium sulfate, here's our sulfates. Where are they? Sulfates. And the exceptions would be these compounds, but sodium is one of those group 1s, so that's definitely going to form an aqueous substance. We see this as a double replacement reaction. Now the barium is going to go with the sulfate, so we're going to get barium, sulfate, and we're going to get some sodium chloride. So barium sulfate, barium is an exception, so this one's the one that's going to precipitate out, form a solid. And our sodium, okay, that's anything here, chlorides are always going to be, so this is going to form an aqueous solution. So I just kind of go through and identify what's happening in my reaction. So now I'm going to come up with my regular balanced equation. So barium is Ba, chlorine is Cl, that's a +2, that's a -1, so there needs to be a 2 there, and this is going to be aqueous in solution. We have our sodium sulfate. Okay, that's also going to be aqueous. So again, +1, -2, need 2 of those. Okay, make our barium sulfate. That's going to precipitate out. That's going to be our solid. And then some sodium chloride. And that's going to be aqueous. So when we look at this, we'd say, okay, we need to make sure it's balanced. We're going to need to put a 2 there. So there's my balanced chemical equation. That's what we've done in the past. Now we're going to make this the ionic equation. So we're going to split this up into ions. So this is my barium ions, aqueous, and my chlorine ions, aqueous. Okay, because of the 2 here, I know I'm going to form 2 ions in solution. So really I'm getting like 3 ions in my solution from this one. Same thing here with my sodium. I'm going to get 2 ions in solution. I'm going to get my sulfate in solution. This one is the solid, that one stays together. And then we're going to have our 2 NAs as ions and 2 CLs as ions. And again, when I show this complete ionic equation, I have to show the charges because those are the ions. And I'm showing the states to show that they're all aqueous. Once we get it to this point, we look for our spectators. And this is pretty easy to see that our spectators are going to be the sodium and the chlorine. So those are the ones that we're going to remove to write our net ionic equation. So some barium ions in solution plus some sulfate ions in solution will make some barium sulfate. Precipitate out. So this is my net ionic equation, my complete ionic equation, and my balanced chemical reaction. I want to just go one more example here, but this one's going to be kind of reverse. So let's say we want to make some nickel, okay, we want to produce some nickel sulfide as a solid out of a reaction. So we want to make that. What could we start with to make this? So if we think backwards, we know that the nickel sulfide, so any sulfide has is going to be an insoluble in a solution. I need to have something that's going to have some sulfide in it that would be aqueous, and I need something that's going to have some nickel in it that would also be aqueous. So I need those two things to be in the reaction as aqueous ions in order for it to happen. It's like I'm making the ionic the net ionic equation, like +2, -2. These ions need to be present in order to make this compound. So it's like the net ionic equation. Now, I have some options because really when it comes to spectator ions, anything will work. So I could use any kind of part here or part here to kind of mix together because they're going to become just my spectator ions in the end. So those are just the leftover spectator ions. So if I look at this, I'm going to say, well, what could I pair together with some nickel to make sure that it's going to be soluble in solution? And the easy one might just be, I'm going to pick a halogen. So I'm going to make some nickel chloride. Okay, some nickel chloride mixed together. And then I need something that can go with sulfur. And this is any of these. So maybe I'm going to choose some sodium. So some nickel chloride plus some sodium sulfide. When they're aqueous, get mixed together, that's going to precipitate my nickel to sulfide, and I'm going to get my spectator ions of sodium and chlorine, or I'm going to make some sodium chloride. But if I look at it from the spectator point of view, I'm really spectating sodium ions and chlorine ions, and I'm going to have probably 2 of those and 2 of those. So I'm kind of working a little bit backwards to kind of figure this out. But it allows us to kind of say, if I want to make something, all I need to know is what were the 2 things that made it. Those have to be parts of the compound that could be mixed with other ions that would be aqueous in solution. And remember, the other parts are actually going to become spectators in the end. So again, this is how you kind of use your green sheet to know whether something is going to be soluble or insoluble. And you can then look at how to create your complete ionic equations and your net ionic equations. If you have any questions, we'll ask them in class.